So I'm just going to talk a little bit about properties of the nucleus. We all know in our regular atom we have orbiting electrons around a central nucleus. The nucleus is tiny compared to the size of the atom. The atom is about 1 angstrom in diameter, which is actually equivalent to 10 to the minus 10 meters. It turns out the nucleus is about 10 to the minus 14 meters. So it's actually 10,000 times smaller. It consists of fermions, which are protons, and neutrons. So these are what make up the nucleus. These have some special properties, so I'll just write here nucleons, protons, and neutrons. So these are fermions, which gives them some special properties that we will be needing later. They have an intrinsic spin s of a half. They have an orbital angular momentum L, which can be 0, 1, 2, 3, or whole numbers from there. And in atomic and nuclear physics, we actually define these numbers as letters. So they correspond to S, P, D, F, and so on. And these letters we'll be talking about later as well. That's something to do with the shells inside the nucleus. So it has this intrinsic spin, orbital angular momentum, which means it also has a total angular momentum. And in terms of quantum numbers, we define this as J, which is the coupling of S and L. And it actually turns out that since it has an orbital angular momentum, the nucleus has a magnetic dipole moment. So that's important in terms of what interactions the nucleon does with other particles. So all these nucleons individually have these properties, but actually what happens is they combine and sort of form these shells where they effectively cancel out. And then often what happens is we have these closed shells with these properties, and then we have maybe 1 or 2 nucleons left as valence nucleons, and they determine the properties of the total nucleus. So the nucleus has a property which we call nuclear spin. And this is defined as I. But actually it's not spin as an S here, we just call it nuclear spin, it's just a name. Actually I corresponds to this J, and I will get back to this. Another nuclear state property is parity. And this is something that depends on the wave functions of the nucleons. And the way it's defined is as pi. It's -1 to the power of the orbital angular momentum. So it can either be plus or be minus. Now let's leave that for now. And what we're interested in looking at now is, how do we define this radius of just any regular atom? Well, there are several ways you can think about it. So size of, well, I guess we want to look at the size of the nucleus, don't we? Question. So one thing we can look at is in terms of matter. And what we can do is do experiments and just sort of estimate the size by bombarding the nucleons with charged particles. Because the protons are positively charged, that and the neutron's actually neutral. But in this case, we're interested in this proton interaction because if they're charged, then they exert a Coulomb force. And if you then send in charged particles, for example electrons, then you can actually measure the strength of this force. And what we find is that there's a relationship like this. The radius of the nucleus is, well, it's approximately equal to R0 times a to the 1/3. And R0 turns out to be measured to be around 1.2 femtometers. Femto meaning 10 to the minus 15, I believe. Another way we can look at the size of the nucleus is by thinking, okay, well, they're positively charged, so can we then look a little bit at this charge distribution? How does that look inside the nucleus? Is it even everywhere? Or so what we do is take a measurement. This is the charge density. And it turns out, as a function of distance from the center of the nucleus, we obtain a shape like this, where in the beginning it's just constant. So if we have our nucleus, grab a different color. This is just a nucleus. When we're near the center, the charge density is constant. And that makes sense. I mean, we have a proportionality between, well, oh, sorry, ignore that. When we get further out, that's when it starts changing, and that's here. So at the surface of the nucleus, it's no longer constant. And one way to then define the size of the nucleus is saying, okay, well, if we start with a charge density in the center called ρ0, then as we move out, let's define it as we get to the edge of the nucleus when ρ has fallen to half of that value. So then that on our graph here corresponds to something called R. We just label it R half. So that's, in this case, that would be this length. And it turns out actually that different methods sort of turn out to give the same value for the radius of the nuclei, and this one is quite a good approximation that is mostly used. It's a bit difficult to get more precise values, but people are working on that. So you can define R in different ways as well. So for example, you can say, well, let's take the root mean square of R instead, but it's still sort of the same order of magnitude and the same size, so we won't worry too much about that. Another thing to think about is that actually this is not always true, and it sort of depends on the atoms, and it's just important to bear in mind that it might vary. And also, we can't always assume that the nucleus is just a sphere. I will discuss this later. And the charge density as well doesn't always look like this. So let's talk a little bit about how we sort of, the language, talking about nucleons and the forces and everything. So in nuclear physics, we like to use this thing called the atomic mass unit. And it's U, and it's defined as 1/12 of the mass, the atomic mass actually, of carbon 12. And it turns out, because it's a mass, this is about 1.66 times 10 to the minus 27 kilograms. But actually, in nuclear physics, we don't really want to be working with masses in kilograms. So we find, we know Einstein's formula. Energy is equal to mass times the speed of light squared. So we get this equivalence or conversion between energy and mass, and that's what we like in nuclear physics, because we're interested in the energy. So it turns out that this is actually equal to, or approximately equal to, 931 mega electron volts over c squared. So electron volts is another unit, a mega electron volts, that we really like to use in nuclear physics because it makes sense in terms of the order of magnitude of things. And this is a really nice unit. Actually, the mass of a neutron, which is approximately equal to the mass of the proton, is about this value. That's nice. And this is about 2,000 times the mass of an electron. It actually turns out that Mn is slightly bigger than Mp, but we won't worry about that now. So, we need some language where we can talk about the strength of holding the nucleus together. And the first thing that we do is to find something called the binding energy. This is defined as the energy mass of the constituents of a nucleus minus the atomic mass of the nucleus itself. So let me just write that down. And because we want energy, we say mc squared. So the c squared is outside here. So the number of protons times, so the mass of one hydrogen atom, is just one proton and one electron. So this is actually all the protons and electrons, and this is all the neutrons. So that's the total mass of the constituents minus the mass of the nucleus that we're interested in. And what this is saying is actually that when nucleons come together and form a nucleus, that nucleus will have slightly smaller energy than all the neutrons and protons separately. So it's because they sort of form this really well bound state. I mean, the protons and nucleons are happy being together like this, and that releases a little bit of energy because they don't need so much energy to stay together. It's sort of, in nature, that's what happens. You find this state where the lowest energy state, so it's a very stable system. And just a comment about this so these are atomic masses. And the reason we use this is actually because that's what we measure on daily life. We don't measure just the value of the nucleus itself, we usually measure atomic masses, so that's what we generally use. Yeah, so just to elaborate on that a little bit, this means the nuclear mass, which is denoted by N, is actually the atomic mass. But we just have to think about, well, what about the electrons in the atom? Okay, you want to take those away. So the number of electrons is the same as the number of protons in a neutral atom. So Z times the mass of an electron. And then we have to think, well, actually, if we take all the electrons away, they also had a binding energy from being in the atom. So we just need to compensate for that. And we do that like this. This is the binding energy of the electron over c squared. That's it. That's how we define the nuclear mass if we only have the atomic mass. But more often than not, our equations actually cancel out in a way so we don't have to worry about the electrons and we just use atomic masses. Another useful quantity to think about is, well, how much energy, so depending on how stable the nucleus is, how much energy does it actually take to remove one proton or one neutron from the nucleus? We define something called the separation energy. And it turns out that actually the separation, so we have something called the neutron separation energy. And this is simply the energy required to remove a neutron from the nucleus we're interested in. And it turns out that this is equal to the binding energy of our nucleus. So I haven't mentioned earlier, but this is just, X is just the element, A is the atomic number, which is the number of neutrons and protons, and Z is the number of protons. This is how I like to write it because it makes sense. Some people also write it N here for the number of neutrons, but of course A is just, or N is just A minus Z, so it's easy to sort of work out. That's binding energy of the atom we're interested in, minus binding energy after we've removed the neutron. So now we have A minus 1, and still X, same number of protons. And if you use this formula above, we can rewrite this in terms of masses if we want to. Similarly, the proton separation energy is the binding energy of our nucleus minus the binding energy of the nucleus where we remove the proton. And actually, if we're interested in knowing, well, will decay happen from the nucleus or not, it turns out that in order for that to happen, we need Sn or Sp to be less than 0. Because if this is negative, then the binding energy of our new nucleus is greater than the binding energy of our initial nucleus, which means it's favorable for this to happen, and the nucleus decays by emitting a nucleon. With this equation for binding energy in mind, we now want to look at, well, what do we actually measure? So a very well-known graph is the binding energy per nucleon. So of course A, the atomic number, is the number of neutrons and protons. So it's per nucleon as a function of the mass number. Gives a shape something like this. It's not very well drawn, but there's sort of a maximum here. So it turns out that actually depending on the size of our nucleus, whether if it goes up in size a little bit, whether binding energy is increased or decreased per nucleon depends on the size. So what we want to do is try to somehow model this, or come up with some sort of description, a mathematical description of what is going on in the nucleus that gives this shape. And what we've done is actually think about, okay, well, we need some expression for the binding energy that can take into account all that we know about what is happening in the nucleus. So, first thing we think about is that here's our nucleus. When we're near the center, in this region, we generally have that the binding energy is proportional to the mass number. So this will be our first term. Some constant, which we are not too worried about, times the mass number. This is called the volume term. But actually, so when we get closer to the surface, this is no longer the case, because when you have a nucleon near the surface of the nucleus, this relationship doesn't hold, and we need a term that compensates for that as well. So that turns out is actually proportional to A to the power of 2 over 3. We call this the surface term. Then we need to think about the fact that, well, the nucleus is full of protons and neutrons. And the protons have this Coulomb potential because they're charged and they're actually repelling each other. So we need to include a term for that, which looks something like this. We call this the Coulomb term. Another thing to realize is that actually the most stable nuclei form when stable when Z is equal to A over 2. So that means the number of protons and the number of nucleons are equal. And we call that symmetry. So we need to include a term for that, which looks like this. We call this the symmetry term. And then the last thing to think about is that actually protons and neutrons have this tendency to couple in pairs. And that means protons and protons want to sit in 2 and 2 together, and neutrons want to form pairs as well. So if you have a nucleus which has, so let me just show you. This is the pairing that we're thinking about. So for example, in a nucleus which has an even number of protons, they just sit happily together, an even number of neutrons. Everything is good. This is the most common element we see because it's very stable. But if we have an odd number of protons, and an odd number of neutrons, well, these two don't really want to be partners. So what happens is that actually the proton, for example, changes into a neutron so that these two can couple together. And that gives us some extra binding energy, and we need to consider that. So we include a term that looks like this. Called the pairing term. And it turns out that this is 0 when we have odd, even nuclei. So that means either Z is odd or N is odd, and then the other is even. And it's equal to +1 when we have even, which I showed here. And it's equal to -1 when we have odd. So now we've considered all this, and what we do with this is that we define something called I'll just do that in another color. The semi-empirical mass formula. And this is defined as ZA is equal to the number of protons times the mass of a proton plus the number of neutrons, and the mass minus the binding energy over c². And the binding energy here is then our long expression that we have obtained. And it turns out that actually this gives us a really nice approximation for this sort of shape. So we can map it onto the experimental data, and it turns out that this is a really good model. And what has been taken into account here is actually different models for the nucleus. And we have, for example, one that's called the liquid drop model, where we model the nucleus as a liquid. I'll make another video about that. The other thing is another model is called the shell model, where you model the nuclear states as shells in the same way that actually electron shells are forming around the nucleus in the atom. So the last thing we want to say, is, well, so practically, how do we measure these masses? And what they used to do was measuring masses. So we want to know if all this is true by measuring the atomic masses or nuclear masses. And the first normal thing to do was using a mass spectrograph. And it works something like this. They took the atoms we're interested in and bombarded them with, for example, electrons to make them into ions. So we get an ion beam. And then we put the beam into something that we call a velocity sector. And that has the details I won't go into, but it basically applies an electric field and magnetic field onto this ion beam, so that when they then pass through to this is called a photographic plate. Basically what happens is these charged ions, they get reflected by different amounts, which means we can then deduce the mass from the amount that they've been bent by the magnetic field. A more recent and sort of more accurate way of measuring nuclear masses is using sort of a clock. And what we do is sort of apply some magnetic fields in this manner, so that we can trap ions in a sort of pocket in the center. And then we apply an additional field, so we sort of apply a frequency in the atoms. And so we can find the point of resonance for the atoms, which then the expression for the frequency is actually proportional to the charge to mass ratio of the atoms. And then we can deduce the mass from there by looking at when this resonance happens as we apply different frequencies. This is of course a bit difficult because it's difficult for atoms which are unstable, because this method works so as the longer we leave it, the more precise a measurement we get. So if they're unstable, they'll disappear very quickly, so we'll have a large uncertainty in our measurement. But it's still a more accurate method than this one.